Hi, and welcome for another episode of Quadratic Sieve running on Java. My name is Ilya Gazman. Let's hack. Alright, so in the previous episode we switched using a multi-polynomial based on Peter Montgomery offer. We also improved login and optimized the magic numbers. We can factor now 200-bit numbers in amazingly 226 seconds time. In this episode, we will see how we can increase our reminder to include values outside the prime base. So far we have been searching for smooth value b. Now let's make the condition more loose and also include the values qb, where q is a small prime number outside our prime base. So it's bigger than our prime base but still a small prime. Once we find such values, let's say qb1 and qb2, we can multiply them together to get a smooth value q power 2 b1 b2. So q power 2 can be ignored. I did some nice updates to the GitHub page. I added docs. Let me show you. Yeah, I created a small summary for all the YouTube episodes for your convenience. Let me know if you like it and if you have any ideas on how to improve it. The Google Doc is also available now on as part of the source code. I just converted that to PDF. Okay, so let's hack the big primes. I already prepared the solution because I got stuck on it for 2 days. I didn't know what's happening, and I'll show you exactly what caught me. Okay. Also, now I will show you all the changes since episode 10, and then we'll switch to episode 11. Okay, so now we're going to use a prime base map. I show you where it's used. Max prime, let's start with that. So I'm just computing a max prime when we are when we are building the prime base. And this is its big integer version. All right. So when we are sieving, and we find a bismuth value, we are calling to add bismuth value. And we're extracting a vector. And then if the value cannot be extracted using our prime base, we return null. I added two optimization in this area. First, if value is smaller than our max prime big integer, then it means that it must be on our prime base. So I'm using a prime base map that I'm computing here as part of building the prime base. And I'm just getting the index, because this is really what we need. We are using the I index of our prime base to map the vector. So I'm using the index from the hash map to map the vector. Bismuth vector data, it's an optimization to save on a, actually no, it's not. We'll get to it in a moment. It's just now I need to return two values instead of one. Instead of just returning the vector, I also need to return the remainder of the big prime. So let's see how that portion works. Switch returns a vector data. For the regular usage, I just reuse this item. I just update the vector data all the time. Since it's working on the same thread, we can continue and use that part. In here, when the value is smaller than p bit lengths, p is the prime that we're currently working on. So we see that the value bit lengths, the square, this is very close to the square root of the value, a little bit smaller than it. So if we already moved after the square root of the value, then it means that p is not going to divide. None of our other primes in our prime base is going to divide this value, because otherwise we would already found it and we would reduce the value to 1. So it means that this value is not be smooth. Now there are two options. It could be a prime, and then we will use the new optimization of QB, or it's not a prime. It's a composite number, and then we return null. So if it's indeed a prime, and check this its prime function, it's well, actually I need to talk more about that function, but I will leave it for the next episode. I will get into more details about how that works. It's yet another optimization for factoring small numbers. I'm only using it here to determine if the number is prime. It's faster than checking on a value is probable prime with certainty of 20 or 15. It's much faster. And since our values are going to be smaller than 64 bits, so our prime base is at most of the size of a million, the biggest value in our prime base. So it means just 20 bits. And with the extra values that we are taking, at most it can take 40 bits. So it's still going to be smaller than 64 bits, and so we can convert it safely to long values. Once we will try to factor much bigger values, then this part of the code will have to change. But meanwhile, this is fast, and this is awesome. Okay, let's see what we are doing once we're extracting a vector. So as I mentioned, the Bismuth vector data is getting reused. And so if the vector data is pointing to the same memory location as Bismuth vector data, it's actually the same value, then we will work as we've been working before. It's a regular Bismuth value. We're just adding it to the matrix. Otherwise, if vector data is not null, then it means that we found a new value of the form QB. We cannot just use QB as is. We need to find another QB, QB2, and multiply them. So big primes is a new class to handle that. And it receives the Bismuth value, the reminder, and this is why we need the vector data to give us the reminder, which is our big prime. It needs the matrix and the prime base size. Let's see. So it doesn't need the size actually. So those items, I'm logging how many big primes we found in total, and then I'm saving all the big primes in a big primes map that maps big integer to the vector. So it first attempts to put the big prime, it attempts to put the vector over the key of the big prime. that method return null if the value is not it's not exists in the map. If it does exist in the map, then it's not actually mapping a new value, it's just returning the current value. So if the current value is null, it means that we just added it, and so we have to do nothing because we only found QB1. But if it's not null, then it's the second time we found such value, or the third or the fourth, and then we can actually multiply those values together, QB1 with QB2, and then QB3, QB4, etc. It's enough to just keep one of those Qs. And then we need to XOR those two values together, and then we can add it to the matrix. So the XOR function here, it's doing a current value. I will talk about get a soon, but meanwhile, you can treat it just a as we had earlier. So current value get a multiplies bsmooth get a. So we are doing the multiplications, and then we are doing the XOR. And then we can use that bsmooth value and safely add it into the matrix. Inside the matrix, I also made small changes, so I updated the version to 4. Essentially, I found few bugs, not bugs, but now we calling to add from multiple places, and we need to call to matrix start and matrix end inside the add method, rather than outside like we had it before. Cool. So this is the optimization. And when I did it, I was so happy, but it just didn't work, and I didn't know why. So after some digging, I found that it happens. Let me show you in a second. In here. So we've been using not that. We've been searching all the time for indexes from the beginning. We've been and I also didn't use this native method. I was iterating over the items, but you can ignore that because behind the scene, having the same performance, it's also iterating over all the bit set and kind of testing them if they're on or off. The biggest difference is that instead of searching for eliminators from left to right, so for this vector, the eliminator would have been chosen to be at the position 1. Now, instead of that, we are doing it from the other side. We will choose it to be in here. And that plays a big role in optimizing the size that the vector is taking. Our vector, it's a bit set, and the bit set size is measured by the last bit. So it will create the size as the minimum amount of words times, yeah, it's times the size of the word, which in this case it's a long. So so the eliminator index is now taken from the end, and that reduces the size of this entire bit set once it's getting eliminated to just that. So it's a huge improvement to the matrix performance. And for reasons which I don't know, the entire optimization did not work with that. So I made another comparison of the outputs. Let me show it to you. So I ran that without the optimization on 200 bits, and the result were it solved the problem in 190 seconds. So it's already an improvement from 226 just by all the other improvements that I added here. But you can see that the metrics took 16 seconds in total running time, not including the big primes. So I'm now printing them as well, and it's found 0 big primes out of 0. Now, with the optimization, the time goes down up to 126 seconds. 26 seconds, our new record for 200 bit values. It's almost 100% speed gain optimization with this improvement. And it shows the following. It shows that it found 6K bismuth values and 4K big prime values out of 86K values in total that it found. So it found 86K QBs, but only 4K of those values had a QB2 pair for them. So the rest were not used. And so 6K plus 4K, it's the 10K bismuth values that allow us to find a solution. Now in the execution without it, it had to find 10K bismuth values. And if we scroll up, we can see that 6K, I think it was 800, happened in 170 seconds. So in 170 seconds, it found relatively the same amount of bismuth values. But with the extra of the big primes that were found, it were able to compute a solution much faster, almost 100, almost 2 times faster. So this is that. Now let's go back to the metrics. Thanks to that optimization, it make it possible. Also use that new APIs that I discovered, well, new for me, in here. Yeah, so I'm using the next bit instead of iterating over all of the values. The implementation is not super clear of the bit set, but I trust them that they have some optimizations to make it slightly better than just iterating over all of the values. The biggest gain of using this that it's much easier to debug. It just show you the actual used the actual turned on bits in the bismuth value. All right, and finally, in the latest change, episode to be renamed to 11 soon, I used polynomial data. So the idea was to save on space. The polynomial data is just getting those values, and then it's computing A on demand. So it's not having A until, sorry, in here. It's not having A until it's actually going to use it. And for consistency, I also moved the computation of get C value into here. So basically, all of the methods are now using a polynomial data, and we are adding a bismuth value. We're just providing those items. The polynomial data is computed once for the entire cycle of the sievings until we change Q. That will hold, and the sieving interval is quite big, and so it saves space for all the bismuth that we are going to find in this sieving interval. The only thing that I didn't took into account is that what will happen if we only find one bismuth value. Then this optimization doesn't really save on memory. It can do the opposite, even make the overall memory use bigger So I'm still not sure if it should be reverted or not. Meanwhile, I will keep it. Awesome. And now let's update that to episode 11. Let's revert this. Go back. Yeah. And we are done. If you have any questions, please ask me in the Facebook group or comment below. And the new GitHub page is available for you. I'm going to add the episode 11 here in a moment. See you next time. Bye.